Hello everyone, welcome back. So in this video we are going to learn about the second type of AM modulator, that is switching modulator. Switching modulator. Okay, so if you are first time to my channel, please consider subscribing. So switching modulator depends on the switching characteristics of the diode. Okay, so it depends on the switching characteristics of diode. Okay, so it depends on the switching characteristics of the diode. Let us see the block diagram for this switching modulator. So it has same as a summer circuit, so for which one input is the carrier signal AC cos 2 pi FCT, and the second input is m of t, the message signal. Okay, so the output is V1. So V1 is equal to m of t plus AC cos 2 pi FCT, which is same as the square law modulator case. So here it is switching device. Switching device. So switching device is again a diode. Okay, so it is diode. The switching device used is diode again. So this, and the output is V2. So this output is again passed through a band pass filter, okay, which is tuned to same carrier frequency FC. So output will be V0, which is of the form of the AM modulated signal. So thus we can say that AM modulated signal is obtained at the output of this switching modulator. Okay, so it again consists of three basic elements. One is a summer circuit which adds m of t and AC cos 2 pi FCT. So V1 is equal to m of t plus AC cos 2 pi into FC into t. Okay, so now this is passed through a switching device which is a diode. So it depends on the switching characteristics of the diode. So the output of the switching device is V2, and this output is passed through the third element, which is band pass filter, which is tuned to carrier frequency, and the output is V0, which is of the same form of S of t of AM. Okay, so the switching characteristics of the diode. So this is very important here. So V1, in V1 there are two parts. One is m of t and the other is the carrier C of t. So always we know that the carrier strength is always, the amplitude of the carrier is always greater when compared to m of t. So the carrier strength is very much greater when compared to the m of t, because carrier signal is a high frequency signal and its strength is more. Okay, so what can we say is this signal which is passed as input to the switching device, this is diode. So operation of diode, since the strength of the C of t is more, so operation of the diode depends on C of t, depends on the carrier signal C of t. Yes or no? So because the strength is more, so operation also depends on C of t. So for case 1, now we have two cases, because C of t is also a carrier signal which has positive half cycle and negative half cycle. Okay, so correspondingly we have two cases. When C of t is positive, that is C of t is greater than 0, then what will happen? So when C of t is greater than 0, so diode will be in forward bias. Okay, so diode will be in forward bias because strength is more, which is positive. So positive given as input to the positive, so diode is forward bias. So when diode is in forward bias, it acts as short circuit. Yes or no? So it acts as short circuit. So when this is short circuited, what will happen? So V2 is equal to V1. Yes or no? So output is equal to input because it is short circuited. Switching device here is diode, so diode is short circuited. So what can we write is V2 is equal to V1 when C of t is positive. Now case 2. So when C of t is negative, that is C of t is less than 0, then diode, so it will be negative, so negative given as input to the positive, so diode will be reverse biased. So diode will be reverse biased, so output will, so equivalent circuit of reverse biased diode is open circuit, so diode will be open circuited. So when it is open circuited, then V2 is equal to 0, since no flow of input to the output, so that is why V2 is equal to 0. Okay, so we have continuous cycles. C of t is having a continuous cycle, so it will have continuously positive negative and so on. Okay, so this is how C of t is there. So this is positive negative and again positive, again negative positive and again negative and so on. Okay, so this cycle repeats. So the output, what can we write the output as? V2 is equal to V1 into Gp of t. Okay, so output can be written as V2 is equal to V1 into Gp of t, where Gp of t is a periodic pulse train. Gp of t is a periodic pulse train, looks like this. Okay, so this is Gp of t. Okay, so this is one complete cycle, so this is 1 by fc, so the frequency is fc, then time period is equal, so time period of this is 1 by fc. Okay, so it will be on for first half cycle, so half of the cycle it will be on, so t is equal to 1 by 2 fc, the output V2 is equal to V1. So for the half of cycle V2 is equal to V1, and for the other half cycle T2 is equal to other 1 by 2 fc, V2 is equal to 0. So this is off and this is on, continuously it will be on and again off. Okay, so continuously on and off with a time period is equal to 1 by fc. So on time period is equal to on t on is equal to half of this, so half of this is 1 by 2 fc. T off is also equal to 1 by 2 fc. So half time period it is on, half time period it is off. So when Gp of t is equal to, so this amplitude is equal to 1. So during on, so that is when C of t is positive, and C of, this is where C of t is positive, when C of t is positive, diode will be on, so it is multiplied by 1. So V2 is equal to V1 into 1. So it will be V2 is equal to V1. So same as this. When it is in off condition, so it is 0, so V2 is equal to V1 into 0, so V2 is equal to V1 into 0, V1 into 0 is also equal to V2 is equal to 0. Okay, so we can represent this mathematically with a periodic pulse train. So this will be the input output characteristics of this switching device. Okay, so V2 is equal to V1 into Gp of t, where Gp of t is a periodic pulse train which is represented like this. Okay, so now the period Gp of t is a periodic rectangular pulse, okay, and we have got V2 is equal to V1 into Gp of t. Okay, so this is what we have got. So this Gp of t which we have represented can be represented in trigonometric Fourier series. So it can be represented in trigonometric Fourier series as Gp of t. So we are going to represent this Gp of t in trigonometric Fourier series, which is given by Gp of t is equal to 1 by 2 plus 2 by pi summation n is equal to 1 to infinity for n odd, so it is valid only for odd, minus 1 whole to the power of n plus 1 divided by n into cos 2 pi n fc into t. Okay, so this is how we can represent using trigonometric Fourier series. So Gp of t is represented like this. So expanding that Gp of t, we'll get Gp of t is equal to 1 by 2 plus 2 by pi into substitute 1. So when you substitute 1, what you will get is cos 2 pi fct. Now substituting in 2, so this will be minus 1 whole, so this will become minus 2 by 3 pi cos 2 pi into 3fc into t. Okay, because n is only odd, we have to substitute only odd values, that is 3 next. 3 plus 1 is 4 only, sorry, so plus only, plus 2 by 3 pi, 2 by 3 pi, so cos 3 pi fc into t, plus and so on. Okay, so higher order values are not required because they are eliminated by the band pass filter anyhow. Okay, so what is V2 now? V2 is equal to V1 into Gp of t. So V1 is AC cos 2 pi fct plus m of t, the addition of these two signals, into this Gp of t. Gp of t is 1 by 2 plus 2 by pi into cos 2 pi fct plus 2 by 3 pi into cos 2 pi into 3fc into t plus so on. Okay, so if you multiply, what you'll get? AC by 2, so first term AC into 1 by 2, so AC by 2 into cos 2 pi fct plus 2AC by pi, 2AC by pi into cos square 2 pi fct. Okay, so higher order terms are not required. So here the frequency is fc, and if you multiply with this also, so fc plus 3fc is 4fc, so it is eliminated by the band pass filter, so I am not writing this. Okay, so this is not required, plus m of t by 2, so multiplying these two, m of t by 2 plus 2 by pi m of t into cos 2 pi fc into t, so this is also not required. So m of t into cos 3 pi fct. Okay, so because the frequency here is 3fc, it is eliminated by the band pass filter. Okay, so this signal V2 is passed through a band pass filter which is tuned to the carrier frequency fc, so the output is going to be represented as V0. Okay, so all the frequencies which are around fc are passed by the band pass filter, and the frequencies which are greater or lesser when compared to fc are eliminated by the band pass filter. Okay, so if you observe the first term, its frequency is only fc, so it will be passed by the band pass filter. So we will write that term AC by 2 cos 2 pi into fc into t. So if you observe here, cos square 2 pi fct can be written as 1 plus cos 4 pi fct by 2. Okay, so cos square 2 pi fct can be written as 1 plus cos 4 pi fct divided by 2. Okay, and multiplied by 2ac of course. So first term will be DC term and second term frequency is 2fc, so this term totally is eliminated by the band pass filter because the first term is a DC term, 2ac by pi into 2, so you'll get AC by pi. AC by pi is a DC term which is eliminated by the band pass filter. Similarly, the second term frequency is 4fc, that 4 pi fc, that is 2fc, so it is also eliminated by the band pass filter. And if you see the third term, it is m of t by 2, so m of t is a low frequency signal as we have already seen, so fc is very much greater when compared to w, so this term is also eliminated by the band pass filter. And the frequency of the fourth signal is fc plus w, so it is around fc, because w is very much smaller when compared to fc, so it is around fc, so it is passed by the band pass filter. So 2 by pi m of t into cos 2 pi fct. Okay, so only these two terms will be at the output of band pass filter. So if you take AC by 2 common, so we'll be at 1 plus 4 by pi AC, 4 by pi AC into m of t into cos 2 pi fct. So this is same of the form s of t of am, which is equal to AC into 1 plus ka m of t into cos 2 pi fct. Okay, so cos 2 pi fct, where the amplitude sensitivity of the modulator ka is equal to 4 by pi AC. Okay, So amplitude sensitivity of the modulator is Ka is equal to 4 by pi into AC. Thus we can say that an AM signal is obtained at the output of this AM signal is obtained at the output of the switching modulator. Okay, so this is how an AM signal is generated at the output of switching modulator. Okay.